All right. We've got ourselves a little OneNote going on here. We are going to, hopefully, I can keep up in chat rooms and everything too. Let me move this. We are going to move on here, and we are going to do some chemical reactions, learn how to balance things along with nomenclature. This will sort of go hand in hand because these are about balancing charges and the like. I do want to double check, when did we have written down that we were going to take our next exam? I don't have that PowerPoint up. Does somebody have our PowerPoint syllabus? Somebody have when we were going to take our next exam?
On the 15th.
On the 15th. So that gives us, next week is off, right? So we have 1, 2. We'll see if I can get it done in 2 lectures so that we can take it on Wednesday. We may have to push something back. We'll see how it goes. I know that I've had to push back my Chem 121 because we lost a bunch of time. So we'll see what happens with us. Okay, so what I want to start doing here is talking about chemical reactions. We just started doing the naming. So we had our ionic compounds, that's metal plus nonmetal, our molecules, which is 2 nonmetals, our aqueous solutions, and that's when we just dissolved something into water. And then, of course, we needed that to distinguish between a binary molecule and a binary acid. That's the one that's dissolved in water. And then, of course, our oxyacids, that's hydrogen plus that polyatomic, and those polyatomics always have that oxygen, hence the term oxyacid. Now what I want to do is start talking about the chemical reactions themselves. So this is all going to be about chemical reactions. Chemical reactions.
Dang, look at you getting all good with writing on there.
No, I'm sorry, I'm like getting all trained up here. All right, remember there were 4 ways to know what happened? Four ways to know a chemical reaction occurred. Uh-oh, I'm not going to say occurred because I always wonder if it's 2 R's or 1. So I'm going to say happened. I can spell happened. What were those 4 ways that we had? Shout them out.
Color permanently.
Permanent color change. Ooh, watch this. Ooh, wait, no, I got this. Wait, ready?
Oh, that is cool.
Thinking that up. All right, next, what do we have?
Gas release.
Gas released.
Precipitation.
All right, the precipitation. That's that solid. And we abbreviated that as PPT. And finally?
Heat and light.
Heat and light. Okay, so when we look at any sort of chemical reaction, we are looking for one of these changes to occur. Now, I'm going to write the general form of a chemical reaction and then give you an example where we'll actually use a lot of the stuff we've been learning here. Of course, I'm going to see if I can click and drag this chat window. There we go. That'll give me a little ruler on that side. All right. I don't know if you guys can actually see my chat window as I moved it or not. So first, writing a chemical reaction. Writing a chemical reaction. What I'm going to do here is I'm going to do the general form of a chemical reaction. Ooh, and I'm going to see if I can do this here. All right, I'm going to go with little a, big A, parentheses, plus little b, big B, parentheses, we'll go to make little c, big C parentheses, plus little d, big D parentheses. Now, as we look at these, the little letters, so our A, B, C, and D, these are the how many's, and our A, B, C, Ds are big ones, A, B, C, D. These are the chemical species, or the chemical compounds. And by now, you guys probably know what these parentheses are going to be for. These are the physical states. And of course, we have solid, liquid, gas, and now our newfound aqueous. It should also be noted, one other thing up here, everything here on the left, these are what we call the reactants. And everything on the right are the products, the things we are making. Until you come to Chem 121, and then we'll find out both sides are both. Now, this is a general form. It doesn't always have to be two things equal two things. It can be one thing. It can be things coming together, breaking apart, you name it. But in general, you'll have a certain amount of things on the left equaling a certain amount of things on the right. And as we'll soon see, we are going to have to recall our conservation of mass when we do this. Now, I'm going to give you an example of one of these. The example I'm going to give is acetic acid, which is HC2H3O2, and that's going to be aqueous. Now, like I said, with the oxy acid, that's always understood, but I'm going to put it here for completeness. I'm going to add to that some sodium hydrogen carbonate. That's going to be a solid. And on the back end, I'm going to make sodium acetate, so NaC2H3O2, and I'm going to note that that is going to be swimming around. I think I'm going to run out of room, so I'm going to put it here, plus CO2 with a gas, and plus H2O as a liquid. Now, as we look at this, a couple of things that I want to point out. In this chemical equation, we actually have a lot more information than you might originally think we have. And all we have to do is basically state the obvious things that occur to us when we look at this equation. First things first, acetic acid, does anybody know its common name? So this is acetic acid, AKA?
Vinegar.
Vinegar?
Yep. And this sodium hydrogen carbonate? Sodium hydrogen carbonate, AKA baking soda. Now raise your hand if you've seen this before. Just kidding, I can't see your hands. But hopefully someone somewhere around 3rd grade decided to make the volcano. Remember the volcano in your little sciencey class? It blew up and it got all fuzzy and whatever.
Yeah, I just did it with my girlfriend's 2nd grade class.
Yeah, and it's just vinegar and baking soda. We've all seen this. If you haven't, get some vinegar and baking soda at home and do it. Now, here's the thing. The reason I point this one out is it's something that we've all seen. It's something we all know and love. When we were kids, we were all wowed by it. A chemical reaction occurred. We didn't know what, but we knew it occurred. And why did we know it occurred? Oops. This guy right here. What did this chemical reaction just tell us? What does that G there mean?
Yes.
Gas.
Yeah.
Disgusting.
So that right there tells us that we will have a chemical reaction. I mean, take a look at it. If the CO2 gas were not released, what do you have? You have a watery solution, vinegar. You have sodium hydrogen carbonate, a solid. If the gas weren't released, look at the physical states on the other side. The sodium acetate is still a liquid, a watery solution, and you make liquid water. You would not have seen the change. You wouldn't have known anything happened, except for that one glorious CO2 being made, something new, a gas being released. So in this equation, in this example, we already know that a physical change, a chemical change occurred. We may not know what, but we know something happened. What we're gonna now learn how to do is to take these equations, learn how to make sure that they're balanced, and then learn how to predict what we're supposed to make on the other side. And we should be looking for somewhere in there, these guys right here, of one of these pointing out that a chemical change actually occurred. So let's talk about balancing these equations. So right now, I just want to point out that the top one that I have written here is actually balanced, meaning what goes in must come out. But let's learn about how to balance things. Balancing equations. And remember, this is what goes in must come out. And that is from our conservation of mass. So let's remind ourselves again. Let's learn how to spell reminder. Reminder, subscripts. Subscripts, these guys will tell you how many of each atom or group. Subscripts tell you how many of each atom or group. Okay, so when we have the subscripts, if there's the parentheses, it's the entire group. The coefficient, that's that blue thing out there. Remember, that's that A, B, C, and D. These will tell you how many of that chemical compound. How many of that chemical compound. I want us to keep that in mind as we do this. Now, I always hesitate when I get to this part. What I'm about to do is to write some equations here and show us how they're balanced. I'm going to go ahead and write them more correctly the first time. We'll talk about that a little bit later. There are some books that write it very obviously the first time, and then you have to fix something later. I'm going to try writing it correctly the first time so I don't have to fix it later. So if you have a weird question and I say, just wait for it, just wait for it. And all will be revealed in about 20 minutes. So here's what I mean by that. Let's do some very easy examples. Easy examples. I'm going to start with things we know. Sodium plus chlorine. What happens when I make sodium and chlorine together? What do I make?
Salt.
Salt. And how do I write that?
NaCl.
NaCl. We all know that sodium and chlorine make sodium chloride. Now, remember that this is because that sodium was a +1, that chloride was a -1. They will get together and balance out each other's charges. Now, I have written the chlorine as a diatomic. We talked about those before, and I said we will definitely see hydrogen and chlorine and oxygen on a regular basis, nitrogen as well, when we do these things. So you need to be aware that when these things are by themselves, they do run as a diatomic. So that's the reason why it's a Cl2 on the left-hand side. Now, what I would like us to do is to balance this. And what I mean is that whatever atoms are on the left better also show up on the right, okay? What goes in must come out. So we can see here on the left that we have 1 sodium, and on the right we have 1 sodium. So far, everything looks good. I'll go ahead and leave that there. Now, here we see we have 2 chlorines on the left and only 1 on the right. Okay? That's a problem. If we have 2 chlorines on the left, then we better have 2 chlorines on the right. So to balance this, what I do is I say, I must not have formed 1 sodium chloride, but maybe 2 sodium chlorides. And so that 2 is distributed across, telling me I now have 2 sodiums and 2 chlorines on the right-hand side. Well, you'll notice now that that means that I have 2 sodiums on the right, which means I needed to come back and put 2 sodiums on the left. So it really wasn't 1 sodium and 1 chlorine coming together, but now 2 sodiums and 1 chlorine molecule making 2 sodium chloride compounds. You guys okay? If anyone like has a question at all, you need to jump in. You need to just shout like you would in class.
Can you explain that one more time, please?
I can. Who was that?
Yadira.
Yadira, thank you. So let me go back to the beginning on it real quick. I'm going to go ahead and erase these guys. So just, you know, the chlorine right here is a diatomic because that's how it comes in nature. All right. That's why it's an Cl2 there. I have 1 sodium and a chlorine coming together to make sodium chloride. I'm going to look to my left. I'm going to see 1 sodium. I'm going to look to my right. 1 sodium. Conservation of mass is upheld. I'm going to look to the left. 2 chlorines. I'm going to look to the right. 1 chlorine. No me gusta. Okay. Now, I believe, yeah, I did. I had blue for the coefficients, so I'm going to stay there. 1 sodium, not a problem. 2 chlorines on the left, 1 on the right. I'm going to now have to make 2 chlorines on the right. So that 2 is distributed through just like in math, multiplying the whole thing by 2. But that also now apparently throws 2 sodiums on the right, which means I probably didn't start with 1, but I started with 2 sodiums on the left. Sometimes I like to think about this in terms of a baking recipe where you're trying to figure out, hey, I need to make a cake, right? And the recipe may call for half of an orange, and you're like, you know, to get some like orange peel on it or something to spruce it up. And you're like, well, I don't want to just waste half of an orange and only peel half of it. So I'm just going to make 2 cakes out of it. So that 1 orange would make 2 cakes instead of trying to cut something in half. It doesn't matter how many you start with on the left or the right, as long as at the end of the day, all the atoms will balance each other out. So that's what we're going for here. Get one here. Let's do
Forrest, this is Reagan.
Yes, Reagan.
So all semester we've been writing NaCl2, and then
We've written NaCl.
we have written NaCl. Okay. Now you're bringing in the.
I have never written this.
Okay, so now we're bringing in the what is it? The diatomics, and that's why we need to put 2 NAs.
Yes. Yes.
Okay, sorry. Thank you.
Yeah. So I'm going to do another one here. Magnesium plus fluorine. If we take a look at this, magnesium has what charge, guys?
Positive.
Positive what?
2.
Positive 2. So I do apologize that I don't have periodic tables there to float around. But hopefully you guys have one up around on your side. It is a positive 2. So that's a 2 plus. And the fluorine is a
-1.
-1. So to balance this compound, what should I do?
You need add a fluorine.
The fluorine is already F2, so it's already balanced.
Okay, good comment there, Sume, but I'm going to talk over the top of you. Just real quick, 2 plus and a 1 minus means I need 2 of those fluorines. Oh man, I find myself covering up my own screen that I would do normally in a normal classroom. I need the 2 fluorines to balance out the +2 charge of magnesium. So right now, this magnesium here is balanced and it's totally happy. I am not looking to the left at all. I really wish we were in a normal classroom where I could cover up the left-hand side and say, I don't care what you see on the left. I just want to focus on building my compound, because this is what we're going to have to do. In order to balance an equation, first we have to balance our compounds, and then we'll figure out what went on. Even in the top example, I said sodium and chloride. What do? You said NaCl. I said, great. Great, I made NaCl. Let's make sure all of our ingredients match our product. All of our reactants match our product, and that was the balancing portion. This first portion of just making sure your your products are all fat and happy has nothing to do with what you see on the left. Nothing to do with what you see on the left. It has everything to do with what are you guys going to do when you get together. I'm going to emphasize this over and over and over again, that when you're balancing your compounds on the right, you don't care about the left at all. Now, having said that, we can agree that this MgF2 is correct. It's written correctly, yes?
Yes.
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 So now what we do is we double check, does our left equal our right? I see 1 magnesium on the left, 1 on the right. I see 2 fluorines on the left, 2 on the right. Are we balanced?
Yes.
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 Yes, we are balanced here. I'm going to make a very large safety tip. I'm going to say this over and over, but I'm going to write it right now. Note, never bring over subscripts. This was coincidental. All right, never bring over the subscripts. You are only going to build your compounds and you'll worry about the rest later. So just because I had the F2 there does not mean that I brought the F2 over. I made it an F2 to balance the magnesium. On the top example of sodium and chloride, I did not bring over the subscript. I built my compound and then balanced it accordingly. So be very careful. Now I'm going to do one that seemingly violates what I just told you, but it won't. Let's say that I have a calcium, and I'm just going to go ahead and put these in ionic form first, and a phosphate. Man, I wish I could get my, oh, I can go up here and I can go like participants. Who do I first see? Fernando, you're the first name I see. Can you tell me what I make on the other side? And if the answer is no, just come in and say no, and I'll go to the next person. Hearing nothing. Carissa, can you do it for me?
Someone in the chat said baking soda.
No, you won't make baking soda this time. Baking soda is sodium hydrogen carbonate. We don't have sodiums. We don't have hydrogen carbonates. We have calciums and phosphates. Calcium, yes. Very good, Fernando. But how would I write that? And if you don't have a mic, that's totally fine. I was just trying to get some people to chat a little bit more. And Carissa left me hanging. So how about, did I see Daisy in there? Hey, Daisy, you want to talk to me?
You want to?
All right, Daisy, you're on. What should I do? We know my two pieces are a calcium and a phosphate. How would I write that?
You put the PO4 in parentheses.
Okay. Why am I going to do that? Remember, we have a 2 and a 3 here, guys. Is it very easy to balance those things out?
It's gonna be 6 calcium, 6 in front of the equation to balance everything.
Almost. The 6 is correct. That is the least common multiple here.
Mm-hmm.
But the least common multiple of 2 and 3 is 6. So how many calciums do I need?
3 calcium.
There we go. So I need 3 of those calciums. And how many of those phosphates?
2.
I need 2 of them. So,
Okay.
you know, in order to save a little bit of time here, I think this is probably the more prudent thing to do. I'm going to stop sharing here for a second. Because I want to get back to where I can see all your hands. I just want to see who I can actually call on, who will actually answer me, because I don't want to waste time. Let's see if I can drag this out so I can get a bigger thing. I can't. So basically, if you're willing to answer questions,
You know, you can put the participant on the side of your page.
sorry?
You can put the list of the people on the side when you share your screen.
Oh, I'm just going to write them down here. I know Sume, Reagan, and April will answer me. Is there anybody else willing to?
I'm here. I'll answer if I can.
Okay.
I will too if I know what it is.
That's fine.
Well, if I know.
I'll try.
Yeah, I'll jump in.
All right, let me move my chat screen out of the way since I got this. We got Nathan. All right, who was that else? And Dom and Shaw. Next person, sound off. Otherwise, it's just those 6.
Destiny.
Destiny.
Is she gonna be there? And Dominic too.
I'll
Okay.
answer some questions.
Vincent, thank you. Yeah, I'm not. I just don't want to have too much dead air. So, all right. So that's enough people to try to get some things. And again, if you didn't raise your hand but you still have that question, by all means, just shout out. I just don't want to wait too long. All right. So again, what we did here is we looked for that least common multiple of 6. We needed 3 times 2 for the calcium to make a positive 6, and we needed 2 times the negative 3, the phosphate, to make the negative 6. Those charges balance each other out. That's why there's no charges written here on the calcium phosphate. It is a balanced compound. Now, at this point, we need to balance this equation. So I look over here, I see that I have 1 calcium versus 3 calciums. So I need to fix that. I'm going to put a 3 in front of that calcium. I see that I have 1 phosphate and 2 phosphates. So I'm going to put a 2 in front of the phosphate. Now at this point, there might be a few of you up there who are looking at my note on the top that says never bring over subscripts, and yet it looks like I kind of did. We see that I took the PO4 and I brought over that subscript of the O4. That almost appears to violate things, but it does not. Remember, this is a polyatomic ion. This PO4 3- is itself. It is a thing. It is a chunk. When you're bringing over a thing, you don't worry about that subscripts because you're bringing the whole thing over, okay? So I'm just gonna put this down, but I'll erase it. But just so you remember, when we did something like nitrate, we said NO3 with a minus, we drew it as follows. And we put a big bracket around it and put a big -1 right there because the whole thing was a -1. So when you see a polyatomic, you bring over the polyatomic subscripts, but you don't bring over any other subscripts, as in the case of this fluorine. We'll be doing a lot more of that. So just be
Okay.
careful. Okay.
Forrest,
Yeah, yeah.
when you on the products, we're doing stuff, so we can write subscripts on the bottom to tell us how many we need, but on the products, we're writing it in front. I'm just a little, I get the whole least common denominator, but why don't we've put 3 calcium, 2 PO4 in front of each of the compounds versus putting them as subscripts?
Yeah, so her question, I think I get your question. Your question is something like this. Why didn't I do this? Something like that. Is that your question?
No, on the right-hand side, why didn't you do 3?
Oh, okay, so first of all, you wouldn't do the thing you just wrote. Why didn't you do this? 3 CA and then 2 PO4s.
Right, and I know that looks goofy, and I've never seen anything.
That's your answer. That is exactly your answer. Your answer is, that looks bizarre.
Stupid. Okay.
And if it looks weird, check yourself before you wreck yourself. All right, so yeah. And the key here is, I like to call it putting your socks on before you put your shoes on. Balancing the compound is putting your socks on, then you're gonna come back and put your shoes on, okay? And that shoes on is balancing everything out. You have to make sure your products look good, and then you come back and make sure the reaction itself looks good. But you don't put coefficients in the middle of a compound. That just looks bizarre, right? You wouldn't say Ca2F. That is just weird. That's bizarre. I don't know. It scares me. I don't want to be scared. Let's do another example. Aluminum plus oxygen. Ooh, I'm actually going to go ahead and do this one in steps. I'm going to do this one in steps to show you my thought process. After that, we're just going to do a lot of talking. And normally, in a normal class, I'd be up there and I'd be pointing left and right. You guys are just going to have to use your imaginations like this is one gigantic Dungeons and Dragons game. All right, I'm going to put these two things together. How would they come together? I know that I have an aluminum part, and I know that I have an oxygen part. But, Nathan, what's the charge on aluminum?
What's that?
You got this. I'll give you 3 guesses.
3.
Hey, very good. Oxygen?
-2.
There you go. All right, so we got a 3 plus and a 2 minus. Least common multiple?
6.
So then how many aluminums do I need?
2.
And oxygens?
3.
All right. By the way, guys, totally fine to do exactly what we just did here on the screen. But when you do your exam, you want to come back up here and get rid of those because those charges are no longer valid. They have been canceled out. Okay. So now what I want to do is I want to balance this. And I think I'm going to go ahead and keep with you here, Nathan, if you don't mind.
All right.
How many aluminums do you see on the left?
1.
And on the right?
2.
So I'm going to do this one step by step. So first I'm going to go ahead and make sure my aluminums look good. So I'm going to say that I have 2 aluminums plus the oxygen goes to make Al2O3. All right, so we did aluminum first here. So now we need to do the oxygen, right?
Yeah.
How many oxygens do you see on the left?
2.
On the right.
3.
Least common multiple.
6.
All right, so then how many of those oxygens do I need?
3.
Okay, and we'll go ahead and finish this out. So I see I have 2 aluminums plus 3 oxygens. We'll go to make Al2O3, but we needed now 2 of those. So now we see, hopefully you guys see that I have 3 times 2 is 6 and 2 times 3 is 6 oxygens. Okay? All right. However, what did I just do, Nathan? We have to fix the aluminums now. How many aluminums did you just now generate on the right-hand side?
On the right, that's now 4.
That is correct, because we have 2 times 2 is 4. So we didn't start with 2, we started with
4.
4. So we have 4 aluminums plus 3 oxygens goes to make 2 Al2O3s. All right, how we doing, guys?
Okay.
So
Yeah,
far,
leave it like that. Let's look at it again.
let's look at it again.
Yes, please.
I never stopped. All right, as I look at this, I see aluminum and oxygen coming together. I know aluminum is a 3+, oxygen is a 2-. So it will become Al2O3 to keep their charges balanced. The first one I decided to look at was aluminum. I saw that there was 1 on the left and 2 on the right. I guess I should annotate this while I'm doing this. I saw that there was 1 on the left and 2 on the right. Therefore, I had to fix it, hence the 2 that we see there in front of that aluminum. Now that aluminum was fine, I decided to look at the oxygens. I saw that I had 2 on the left and 3 on the right. Least common multiple of that is 6. So I needed 3 times 2 for that oxygen there and 2 times the 3 for the oxygen there to balance out those oxygens. However, when I did that, I noticed that I now had 2 times 2 is 4, and over here I still only had 2. So I had to change that to a 4 to make it work.
Now, is that the final part of that? Because it looks like there'd be a bit more, because the oxygen on the left doesn't look the same as on the right.
What do you mean doesn't look the same? Oh, I love this. Who was that?
Nathan.
Nathan. I love this question. What do you mean doesn't look the same?
On the left it says 3O2, but on the right it only says O3. And
Ooh.
if the...
Oh, sorry. Let me, maybe I screwed up my thing here. 2 O3s.
Oh, let's see.
So 2 times 3.
Yeah.
Sorry, I accidentally kept it in black. Forgot about that.
Do we need to put the parentheses?
No, since this is a singular atom, you don't need parentheses. You only need parentheses when it is a polyatomic, when you need a group of that thing. Singular atoms do not need parentheses, will not have parentheses, do not put parentheses.
Will it appear on the exam the same way as you're writing it now?
What do you mean?
Well, like when you go to...
Oh, this is your question on the exam. Aluminum plus oxygen. What do you make? Balance it. That's what it's going to look like.
Okay.
You're going to end up being like, okay, I can predict this. I can balance my product, and then I can balance the reaction. And then, I mean, for Pete's sake, we're going to get down to where you're going to tell me that's a solid and that's a gas, and aluminum oxide is going to be a solid on the other. You're going to tell me everything. Everything. And it will be glorious. All right, let's do a couple more here. And then
Hey,
I'll probably-
Forrest, this is Reagan. I'm always embarrassed to ask, but I'm hoping someone else may have had the same question. So aluminum. I feel like I'm stuck on aluminum because I know how to get my charges on groups 1 and 2 because they give, and groups 13 to 15 take. 15, 16, 17, and 18 are easy. It's 13 and 14 where I go back to my notes and we have NA, but then I have a note that they want to be like the noble gas. So I'm
No. So that NA was saying, we aren't going to mess with that because if you take a look, especially group 14, aside from carbon, which we've just spent like an entire exam showing you how carbon does not give, does not take, but only shares.
right.
So no charges. And then immediately below that, it's green. Those are the semi-metals. Well, who knows what the heck they do. And then below that, you turn into metals. And I believe, I don't have a periodic table in front of me, but that column includes tin and lead.
Yep.
And tin and lead, they can either take a +2 or a +4 charge. They don't behave, which is why I said, we're not going to predict off of group 14 because you cannot predict. You don't know what they're going to do. I said the same thing for group 13 because you immediately get to a semi-metal, a boron, and then you get to the people under the stairs. Now, that being said, I said there were 4 exceptions. And one of the 4 exceptions was aluminum, zinc, cadmium, and silver. And they have a charge of 3, 2, 2, and 1.
There they are.
Right? So
Yeah.
that's why you knew what aluminum would do. Because you memorized it.
Apparently I didn't. But thank you for the reminder. Now I will.
I was just reminding you that you knew it. I know. All right. Let's do a couple, 3 more, and then I'm going to give you guys one for homework as we start moving forward. Because I don't want to take, normally I take like a good 10 minutes or so for you guys to do this and walk the class and see the common errors. But I think I'll give it as a homework and we'll pick it up on Monday as a, what did you guys get? So let's do some more examples.
We have
I wanna
vacation
do-
starting Monday?
What? Oh, a couple Mondays, you know.
Oh, okay.
Unless you guys want to power through, because I know you guys love this class like more than life itself.
Like we have anything else to do. I mean, I'm not saying it. I'm just.
Right. What are we going to be doing?
Yeah, I'll just drink more.
I will tell you this, there's been much talk about people going like, hey, can we just teach through spring break? And while I would say plenty of people are on the mindset of like, we ain't fucking going nowhere. Why not? I guess legally we're not allowed to. So we've been legally advised to just sacrifice education and let you guys get bored. So,
Sounds about right.
I mean,
What
unless
if you held office hours through that time and we got on and just went over a few examples to get, more educated on it?
I have discussed with the wife about doing a little bit of work here and there. So if people do want an office hour, in fact, let me go ahead and get my participant list. I don't know if I can see all the hands here. I think that's where we see it is in the participant list. Hands about people that would come to an office hour or 2 during the week of spring break.
My hand is up.
April, Fernando, Vincent. So plenty, enough of you. That I'm good. That's all I needed. I don't know. As long as I had 5 hands, I was going to call it. So what I will do is I'll set up some sort of day or time and go from there. And I may just make it. Well, we'll talk at the end of class about when I make it. All right. Let's take a look at this. We have alcohol plus oxygen. We are going to burn that stuff. And at the back end, we're going to make carbon dioxide and water. This is a combustion reaction. You'll be able to recognize that here soon. What the heck happened over here in the chat? My chat blew up. What happened here? Is there a thing? Okay, people were just impressed. Okay, good. I would be impressed with Nathan too. He's a rock star. Okay, so eventually we will learn that on a combustion, you're going to make carbon dioxide and water. We will recognize combustion because you're going to have some sort of hydrocarbon with oxygen blowing themselves up. But for now, we don't care. I'm going to give you this and just say, just balance this. I don't care, just balance it. So I'm going to make my ever so confident Reagan balance this one for me.
Okay. Well, the first thing is we brought over a subscript and we weren't supposed to.
Did not bring over a subscript.
The O2.
Now, I'm glad you said that because we have done this. How many times have we drawn CO2?
Oh, numerous times. So that should count as one.
We know what CO2 is. Hold on, Reagan. Reagan.
Yeah.
Where's your subscript you brought over? Where is it? Do you see anything?
Oh, yeah. Oh, we brought over the O2.
Where?
I don't see anything on the left now.
That is correct. And that's exactly what I want you to do. You did not see an O2 on the left-hand side. What you saw is, hey, I'm going to make carbon dioxide and water. And I will write carbon dioxide and water. And then, and only then, will I go back and make sure everything is okay.
Okay.
All right. So let me be very clear because you know, when I did this reaction, aluminum plus oxygen goes to make. And I said my pieces are aluminum and aluminum and oxygen. Okay?
Yes.
At that point, you should be like, great. What do I make? Oh, well, I know that's going to be a 3+, and that's 2-, so that's going to be Al2 and an O3 to make my 6. And then these will magically reappear once again, and then you will balance your equation. Okay?
Yes.
And I know it's weird for people to do this, and they always want to look to the left, and it gets a little weird. Once you put your stuff on the right-hand side, just make your right-hand side look good, then look back over to your left side and balance the equation. We did not bring over the subscript for CO2. We made CO2 the way CO2 should be made.
Okay.
So,
All right, well then, so from balancing, if I look at it right now, it looks like I've got 3 oxygen on the left.
let's start with something easy.
Oh,
I always do those oxygens last. Those oxygens are crazy.
okay.
So we see
2 carbons,
and
only 1 on the other side.
okay, so therefore I need to put a
Carbon on the right. 2. Yes, I'm sorry, 2 on the right.
I knew that's what you said.
Well, no, I forgot 1's implied. So I've got 2 carbons on the left, 2 carbons on the right.
Okay, now let's take a look at our hydrogens.
So
How
I
many
have
hydrogens on the left?
6 on the left,
You guys all see that? There's 6.
Yes.
and I have 2, right?
So is there an
Where did
easy?
that CO2 come from, though? I don't understand.
Where's the 2?
No, the CO2 and H2O. How did you get that?
Oh, I told you, I will teach you.
Chemical reaction.
We're just balancing. I'm not teaching you how to predict yet. We're just
Oh, okay.
We're just balancing. I just said that's what you make. Now let's balance it. All right, so we had 6 hydrogens on the left. We have 2 on the right. Reagan, is there an easy way to make that 2 hydrogens on the right become 6?
3, yes, add a 3.
Put a 3. I don't like the add. We are
So put a 3.
Every single one of these is multiplying. So you can say put a 3, write a 3, but don't say add 3 because it implies that we are just throwing some up. We need to multiply. Okay. So now, how many oxygens do you see on the left?
We now have 6.
On the left?
6.
3. 3.
Hydrogen. I'm sorry, I thought you said hydrogen. Nope.
3.
Let me go back. Hydrogen is 6 on the right and 6 on the left. Now let's go to on the right. We have 5 oxygen. No.
3.
One on the left. Reagan, your other right. The left.
Oh, the left we have 5. No, 1 oxygen. Looking at the wrong one. 1 oxygen on the left.
3.
3.
Oh, plus CO2, 3. And on the other, on the right, so 3 versus
3.
3 and 4, 7. Yeah.
Okay.
So we have 7 and 3.
Now, is there a way for us to get just 7 on the left?
Oh, yeah. Add a 2 in front of the O2.
Add
3.
a 3 is
And I put a.
against people. Do
I
not-
confused myself. I got it.
So let me back up so
Yep.
the rest of the people are like, oh, what just happened? Okay.
I get it.
So let me back this up. Hopefully you guys can see that on my oranges here, I had 2 carbons and 2 carbons, so I needed to put the 2 in front of the CO2. I went to for my hydrogens. I had 6 on the left. I had 2 on the right, so I'm gonna put it 3 times 2 right here, 3 times 2 to make 6 hydrogens. And then I'm gonna look at my oxygens. I see that on the left-hand side, I have 3 of them, and on the right, I have 7. For those who aren't seeing that, I have 2 times 2 is 4, 3 times 1 is 3. Those will give me 7 oxygen. Now, on the left-hand side, I need to get 7 oxygens. Keep in mind, your oxygens come from all sorts of places. One of them is sitting right there. So that means I really only need 6 more oxygens to make this work. I can come over here and say 3 times 2 is 6 oxygens plus 1 makes 7. And so now everything is balanced. Besides Reagan and April, are we okay?
Yes, we okay.
Yes.
Got it.
Yes.
Anybody else not okay? All right. I say that affectionately, ladies. If you're confused, we can sit after class. We'll do a whole bunch more. All right. Let's do K plus HOH. On the other side, I'll make KOH and hydrogen, which I'm going to write as H2. Why am I writing it as H2?
Diatomic molecule.
Diatomic, very good. Okay, who said that?
Massey.
Massey. Oh, guess who just volunteered to balance this one?
Oh, okay.
Look at her. I got this.
It's already balanced, Mr. Quinlan.
Is it? 1 potassium on the left, 1 on the right. All right. How many hydrogens do you see on the left?
Oh, 3. Sorry.
Right. So even if you just bean count, you see 3 here and you see only 2 here. However, I would like us to take a look at something here that might make our lives a little more better. Take a look at this. I see an OH and an OH. Do you see?
Yes.
Yes.
So I have 1 OH on the left and 1 on the right. So that's good. But then, how many H's do I see?
2.
On the
Oh.
right, but only 1 on the left. Therefore, I need to put a 2 to balance out my hydrogens. But what does that do, Massey, to my OHs? On the left, I have,
2.
and on the right, I only have.
1.
So therefore, I need to
Add a 2 to the. Put a 2, sorry.
But
And
what
then
does
you-
that do to my potassiums on the right?
Yes, so you have to put a 2 in front of the potassium.
Okay, so I love how no one just answers my question and jumps to the answer. It is very important you watch what I did here, because this is how you can balance most effectively, in my humble opinion. Let me back up and notice how I do this. Whenever I balance an equation, whenever I balance all my stuff, I do it in such a way that as I fix something, oops, as I fix something, if I break something else, I quickly fix it. So again, watching here, 1 potassium on the left, 1 on the right. 1 OH on the left, 1 on the right. 1 hydrogen on the left, 2 on the right. Okay, well, that's easily fixed. I'll make 2 of these waters, but that gives me now 2 of the OHs. I don't want that, so I'm going to fix that. Notice I broke my hydroxides, my OHs. I will now fix them. I didn't look anywhere else. I broke it and fixed it. I fixed my OHs, but I broke my potassiums. So now I'm going to fix my potassiums. And hopefully you notice that what I did is I went left, right, right, left, left, right, right, left. It's almost like a tennis match. I don't go left, right, left, right, left, right, because when you jump around, you will a lot of times skip over an atom that you didn't notice or didn't see or didn't care about, and then just assume that it was fixed. Anytime you fix one and it breaks another atom, fix that atom. Okay? Let's do another one. Let's do calcium carbonate plus acetic acid, HC2H3O2. On the other side, I will go ahead and make Ca parentheses C2H3O2, 2. And I will also make some H2O and CO2. Okay, Destiny.
Yep.
I was going to say, suddenly you got really quiet. Are you intimidated by this balancing of an equation?
Yes.
All right, what I'm going to do is I'm going to pour myself some magical coffee, and I'm going to perform a magic trick for your very eyes. So what I need is for you on that side of your computer, because I can totally tell whether or not you're doing this, is I need you to close your eyes. Are they closed?
No.
Lie to me. All right, open up your eyes. What do you see?
C2H3O2 on both sides.
You would display your awesome superior nomenclature power and say, I see an acetate on the left.
Vinegar on the left, on the right also.
Acetate.
So check it out. If you see a polyatomic on the left and you see it on the right, guess what it probably did? It stayed as itself. So what you can do is a nice little, instead of like trying to count all these atoms individually, is you can balance your polyatomics as a group. Remember, guys, up here, we left that PO4 group because it is a group. So if you balance that group, you should be looking pretty good. So if you would, Destiny, how many acetates do you see on the left?
1,
How many do you see on the right?
2.
Therefore, what?
You need to put a 2 in front.
Of?
The hydrogen acetate.
Or acetic acid, yes. Okay. Now, let's go ahead and take a look. How many hydrogens do you see now?
2.
How many do you see here now?
2.
So those look pretty good. How many calciums do you see? On the left.
1.
And on the right.
1.
All right. Now at this point, I want to point out that you see a carbonate here, but I don't see a carbonate on the other side, do I? I don't see a
It's 11
C3.
o'clock.
It's balanced already.
And why do you say that?
Because there's the oxygens on both sides.
Right, I see 3 oxygens. 1, 2, 3, and I see 1 carbon and 1 carbon. Now, at the end of the day, guess what? Sometimes, guys, it is just that easy. Sometimes when you balance one thing, the whole equation just fixes itself. Oh, April, tell me how you really feel about this. Yes, I have the chat window up. April, why do you hate this?
Because it's awful. I don't get it. I'm not understanding.
Anyone else? Raise your hand if you feel like April.
I feel
wait,
like
I need to get my participant list up. Hold on. I need my participant list. How many hands went up here? 6, 7, 8, 9. The whole class got it. All right, guys. So if there's like 10 of you that suddenly raise your hand and go like, I don't get it. This is stupid. Why haven't you guys all like jumped in and said, hey, what's going on? All right. Let's talk about this again. April, what was wrong with this example for you? What's the problem? What's the problem?
I don't know. I just don't think I'm understanding it. I don't.
Can I propose something, please?
Go for it.
How I understand that this time, I use that like cookies. There's a group of cookies, I recognize them. There's a biscuit on the side and chips. Every time I want to balance to make one cake, like the one we do for the snack for the kid, I look at it. Let's say the acetate is the cookie I recognize. I'm moving on one side. If I want to add the cookie on the side as a snack, I need to have the same number on the left and on the right. And I try to balance to see. When I see something is not exactly correct, I have to go check myself again and see. Because if you look all the way to the number of the, let's say, a carbon, the hydrogen, you're gonna make a mistake. But when you see that one as a one group, I remember when you say to us to write the name many times and recognize the molecule or the polyatomic atom. When you do that again and again, you remember that what I already see before. So I use that as a one solid block to move down the one side to the other. I don't know if that helps.
And that's what I was trying to say is as you start recognizing your polyatomics, and I'm going to scroll back up here again to that calcium phosphate. When I look at this calcium phosphate, the thing, when I moved it to the other side to balance my compound, I left it as its chunk, hence the parentheses. Okay? So what I did on this side is I looked in and I said, look, I see this C2H3O2 here, and I see it on the other side. Well, I'm just going to make sure that those balance each other out. And so when I did that, I said, look, there's no reason that that thing would split apart and do anything weird. If I see it on the left and I see it on the right, just go ahead and balance those. So I notice I have 1 on the left, I have 2 on the right. So I need to put a 2 in front of the 1 on the left to make sure that I have 2 equals 2. Okay, April?
Okay.
Now at that point, by the way, I do want to say here that all of these hydrogens here in the middle are already taken care of. I don't need to look at them anymore. They're taken care of. It's these hydrogens that I have to worry about. And oh, look, there's 2 on the left and there's 2 on the right. So I've essentially already taken care of, as far as I can see, oops, wrong button, is I can see that I took care of everyone in here. I don't have to worry about that one anymore. So then I move to the rest of the atoms. I see a calcium on the left and a calcium on the right. We're good. I see a carbon on the left and a carbon on the right. We're good. I see 3 oxygens and 1, 2, 3. We're good.
Okay.
Now, keep in mind, we are going to have a lot of practice on this. The lab is full of examples of this. We're going to be balancing a lot of equations there. we'll balance equations as I write the types of reactions here soon. So we're going to have plenty of experience here. Now, what I want to do next is give you guys a little bit of a homework to try on your own. And I'll be around this afternoon at 1 o'clock for anybody who wants to pop in and see if they did this right. So a little for me to try. I want you to try NH3 ammonia plus oxygen, good old-fashioned O2, making nitrogen monoxide and water. So not now, but after we're done, I want you guys to try that. Now, given that we have technically only one more lecture before we go to the next exam, I want to get into the types of reactions and how we can identify them so that we can have a little bit better time on the Lab 7, which, by the way, just went live yesterday. This lab will help you identify the types of reactions and see them. And then, of course, the whole post lab on this is all about this balancing we just learned. So go ahead and start taking a stab at it. And then we won't have that due until the day of the exam.
So we only have one more class before the test.
Yeah.
Oh,
I think that sound was you actually fainting.
Can I give a little shout out? And Emily just said the same thing. I, until last week, had not gone to the SI hours, and it was just my own fault. I didn't think I had the time, but now I have nothing but time. I learned so much. I haven't been to Melinda's yet, but she's got them. Zahara literally taught me, I felt like she re-taught me what I had learned, and it was probably the most helpful hour and a half, 2 hours I've spent. So if you're not sure of when they are, look on the announcements or look in email. They've been sending them. I cannot tell you how helpful they are. So if anyone's nervous, don't think you only have one more class. There are options to go over this. Okay.
Yeah, come to SI. The plan was to work on Lab 7 and the post-lab questions where we're going over all these reactions this Friday. So, yeah.
I agree. Going to those SI sessions are good. She does actually give a different perspective. The reason why I hired her. She is excellent. So if I'm not around or you just want to see it a different way, by all means, Meng is the best. That's why she's helping you guys out. Classifying reactions. We have 1, 2, 3, 4, 5 different types of reactions that we want to be able to classify. Just like we were classifying with nomenclature, if we know what we're looking at, we know how to build it. So let's take a look at the different types of reactions that we have. The first one we have is the combination. Now the combination reaction in general looks like A plus Z going to make a compound AZ. It's just elements combining to make compounds. Elements combining to make compounds. And keep in mind, most of these you actually sort of have an intuitive basis for. I mean, we've already seen examples of this. Of course, we just had 2 sodiums plus a chlorine going to make 2 NaCl's. We had 2 elements coming together, smashing together, making a compound. Pretty easy. You might have something like good old-fashioned hydrogen and oxygen. Dominique, can you think of what hydrogen and oxygen make? What are you waiting for? There you go. Right, and of course, if we were to balance this, I could look and I could see my 2 hydrogens on the left and 2 on the right, my 2 oxygens on the left and 1 on the right, which would mean I need 2 of those waters, but I messed up my hydrogens, so I need 2 of those hydrogens.
Can you bring the screen back up a little bit, please?
To there?
Yeah, thank you.
So again, you see sodium, the element, chlorine, the element coming together to make the compound, hydrogen, the element, oxygen, the element coming together to make the compound of water. In each of those, the sodium and the chloride should be intuitive. You can predict that. Those are based on charges. Hydrogen and oxygen, that should be kind of like an experience thing. Usually, well, actually for our class, always, our combinations will focus around the metal nonmetals where you can predict what is going to happen. One other one that I like to use a lot, even though it's not one that you would necessarily know immediately, is hydrogen plus nitrogen. It's a good old-fashioned H2 plus N2. On the back end, this would make ammonia or NH3. Again, if we're going to practice some balancing here for just a second, we see 2 hydrogens on the left and 3 on the right.
Why on the first 2 did you put them like how they were, and then on the last one you put the N before the H?
Remember, how does this normally go? Aside from, well, remember when we were building the compounds, we said, how do you know who's in the middle? And it's the one that makes the most bond or the one that is first. Usually, aside from water, the thing that will make the most bonds is put first.
Okay.
So we have 2 on the left, 3 on the right. Hopefully you guys realize the least common multiple is 6. So I'll need 3 of the hydrogens and 2 of the ammonias. But let's see how that looks with our nitrogen. I see that I have 2 nitrogens on the right and I have 2 on the left, so we are good to go. And that is a 3-1-2 balancing. But again, the emphasis here is that you'll have 2 elements, you'll just smash them together. So combination, you have 2 single people, they're going to come together and combine to make 1 singular person. If you can combine things, you can break them apart. That is going to be the decompositions. So the next one here is decomposition. And that is going to look like some sort of compound, say AZ, breaking apart into A and Z, or multiples thereof. And this is one thing breaking down into many. One thing breaking down into many. Now, in general, these are usually unpredictable. Usually unpredictable. Of course, we have an exception. Usually unpredictable, except there are 2 that can be predicted. 2 that are predictable. And that is the following. 1, you will have a metal hydrogen carbonate. And that is going to break down usually with heat, often given the symbol of a little delta across the top of it. When a metal hydrogen carbonate breaks down, it becomes the metal carbonate plus CO2 and water. So this one is very well understood. For anyone who bakes, you do this all the time. What's one of the things you put into anything you bake? It's a powder and it's white.
Baking soda.
Baking soda.
Baking soda, often called, yeah, baking soda. I mean, you're baking with it, right? So the example of this, of course, is sodium hydrogen carbonate. That'll be a solid. On the other side, you'll make the metal carbonate. So that's sodium and a carbonate. I'm going to leave it as just the pieces here for a second, plus CO2 and water. And if I were to be very careful, I would note that each of those is a gas and this last one is a solid. Now, I can't tell how many people are following along by writing in their notes or not, so I'm going to stall for just a second, just in case Reagan is doing this. We have NaHCO3 on the left. On the right, we're going to build our things. And I said on top that it is going to make a metal carbonate. And since we have been studying our nomenclature, we see that that's the carbonate and that's the metal. Now, Reagan, let's make everything on the right look good.
Okay.
What's the charge on a sodium?
The charge on the charge on sodium is +1.
And carbonate?
So C is, oh, well, carbon is neither, so I would have to do oxygen, which is -2.
Remember, they're both negative, so we just have to memorize these.
Okay, negative, so -2.
+1 and a -2. Why is an H2O a liquid? Destiny, I'll come back to that in a second. Sodium carbonate, +1 and a -2. Least common multiple is?
6.
Of 1 and 2 is?
Oh, 2, I'm sorry, I was looking
Here
for
we go.
2. So put a 2
I
there.
need 2 sodiums. Okay. Reagan, can we agree that CO2 is balanced?
Yes,
Yes. Can we agree that water looks like water?
correct.
Okay. Destiny, what you don't know about this reaction is that when it decomposes, you see that big delta up there where I said heat. Guess what? We're making this so hot that actually the water that comes off will actually be water vapor. It may later condense back to liquid, but because we're pumping in so much heat to begin with, it is going to come off as a gas. That's why that one happens to be a gas. Now, Reagan, can we agree that we built everything on the right correctly? Say yes.
Yes.
Okay. So now we're going to go back and we are going to look at our original ingredient on the left.
Okay.
Okay.
So on the left, if I start with sodium, I need 1 more sodium on the left. So then, well, I need 2 total. So I would put a 2 in front of the Na.
Okay.
And what that does is it gives me.
Now, what's interesting here is decompositions are one of those where you actually have to bean count, because what you see is you have a hydrogen carbonate here and no hydrogen carbonate on the right-hand side. So I can't bring that HCO3 and just look for it on the other side. Here, I have to bean count. So how many hydrogens on the left?
2.
On the right?
2.
Okay, how many carbons on the left?
Now 2.
And we have?
2 on the other side.
Okay, and what's my other color I can use here? Purple. How many oxygens on the left?
6.
And on the right?
7, no, 6.
There it is. Sometimes, guys, it's that easy. Okay. Now, interestingly enough, this can continue on, and this is also well understood. You can have the metal carbonate if you continue to heat. If you take that metal carbonate and you get some more heat here, again, with a little delta sign there, this will break down into the metal oxide plus CO2. So I'm going to go ahead and continue this, and let's just say that we had Na2CO3, a metal carbonate. That will break down to the metal oxide, so we have sodium and an oxygen and CO2. Now we know CO2 is a gas. I'm going to go ahead and tell you that the oxide here is a solid. Now, again, not looking at the left, only looking at the right. The charge on my sodium is a +1. The oxygen is a 2-. Therefore, I need 2 sodiums to balance out the oxygen. And now we'll go ahead and look left to right. I see 2 sodiums and 2 sodiums. I see 1 carbon and 1 carbon, and I see 3 oxygens and 1, 2, 3 oxygens. And guess what, guys? Sometimes it really is that easy. Sometimes it just balances itself. Now I'm going to go ahead and, in full disclaimer, decomposition, these two are the hardest ones to try to remember. So how do I put this? These are these are the ones that if you get these, great. If these are the last thing you end up learning, great. I would rather you be able to recognize a whole lot more about the predictions and just be able to identify that this is a decomposition than spend a vast majority of your time understanding these two to the negligence of all the others. So I would recommend these be the last ones that you try to memorize and understand, okay? That's a little safety tip for when you get to exam time. All right, so we have combination, decomposition. Let's talk about single replacement, double replacement, and neutralization, and call it a day. And on Monday, we'll pick it up with the reasoning behind. So single replacement. Okay, with our single replacement, this looks something like A plus BX, and on the other side, it's going to make B plus AX. They are going to switch partners. One element will replace another. One element will replace another. And you guys will see this in the videos that Josh and I did. So this will be magnesium solid plus some HCl AQ. Now in this case, it's always going to be the metals doing the switcheroo. It's always going to be the metals trying to replace one another. And so what this would look like is this magnesium is going to go over and partner up with this Cl on the other side to make MgCl2, which is going to be floating around, and good old-fashioned hydrogen gas. So one of those elements replaces the other, and that element is now formed, which means you should be seeing some hydrogen gas evolving from this. I'm going to go ahead and balance it for you. one magnesium on the left, one on the right. I had one hydrogen on the left and two on the right. I went ahead and balanced that out by putting two. That messes up my chlorines. Oh no, it actually fixes them. You'll find that your last sort of quote screw up will fix everyone else. Another one. Oops. Copper plus silver nitrate. Now the silver nitrate will be floating around for reasons we'll talk about later. Again, this metal will go over and take this non-metal from the silver. And you wouldn't know this. I would have to give this one to you because copper does not behave. I would have had to have told you what it does. And it turns out that it's actually copper 2 nitrate. And solid silver precipitates out. And skipping to the end on that, we'll have to put 2 and 2. But again, what you see here is that you have one person all alone, just like me at the high school dance. Finally getting that one person to dance with me, Wendy Hill, and then Brent Durkin. Can't handle it, just comes over and cuts in. My one chance, spoiled. So sad. Yeah, Freddie, you been there? Been there with me? That was my entire high school existence. Oh, moving on. So single replacement, you'll recognize them because there is one person who is single in this equation, and there's going to be someone else that they can cut in. If you can single replace, you can, of course, double replace.
Can we have another example of single replacement, please?
You're going to have plenty in the lab. And I was going to write this one down, but it was going to be a rehash. Look at this. There's another single replacement right there. The K went over to the OH. So you already had one up top. And again, if you need some more, we can do some more in office hours, or Meng can come up with a bunch. And we'll do some more when we talk about the reasonings behind it on the next Monday. So we'll do a few more even then just to sort of show you what's going on. So double replacement. All right, this is going to be 2 aqueous forming a precipitate. 2 aqueous compounds. Forming a PPT. Reagan, you're doing the homework or not? I can't enforce it anymore.
No. I was saying, I know you're not enforcing it. If people are looking for examples.
Well, go to your homework and do some. Yeah.
Yeah, if anyone's saying, do they need more examples, they'll be in the homework.
Oh, I see.
That's what oh no, I know we're not checking it. I'm just saying if people are looking for examples to play around with, that's a good idea.
Oh yeah, absolutely. I mean, that's the whole point of homework, right? You go home, you try to do the homework, you're like, hey, is this right? You get into an office hour with me, you say, hey, I was doing this, I'll put it on the OneNote, I'll walk you through it, and if you did it right, great. If you didn't, we'll talk about what happened. So yeah, absolutely, Reagan, good call. This would look something like AX, that is aqueous, plus BY, that is also aqueous. On the other side, you're going to form another aqueous and a PPT. Now, I'll go ahead and put here It can be either or any of them. I'm going to put a couple of them down here so that we can see how this might work. And I'm going to go with NaCl aqueous plus AgNO3 aqueous. And this is how you recognize the double replacement. You have two couples on the dance floor. They're going to switch partners. One of them is going to get tired and sit out the rest of the dance. Okay? Now, when you see the two couples, you'll see them here. You got 1, 2 couples. You want to think of a good old FOIL method for math. Yes, more math. FOIL method, as you might recall, stands for first, outer, inner, and last. And that's what I want us to think about as we do this. It will go from the first element to the outer and from the inner to the last. And I like drawing it in this clockwise fashion to remind you the order in which you write them, so you don't write something that looks very bizarre. So on the other side, you'd have NaNO3. And I'm going to tell you right now that that's the aqueous. And you're going to have AgCl, and I'm going to tell you that that is the solid. I'll tell you why on a couple of Mondays from now. But here we see we have two aqueous, we have another aqueous, and one of them turns out to be the solid or the precipitate. Just to remind us, sodium was a positive, nitrate was a negative, silver was a positive, chloride was a negative. I always start out with the trivial example for you so that it's easy to sort of wrap your head around. And I'll move to a less trivial example now. Here we're going to have MgCl2, aqueous, and potassium phosphate, K3PO4, aqueous. Again, we see that we have two couples. What we need to do now is figure out how they switch. Double replacement uses the FOIL method, first to the outer, inner to the last. Ooh, and Vincent, I haven't called on you. Are you still with us?
I'm here.
Perfect. So as I've done this FOIL method, I want us to put our pieces down. So my piece, is a magnesium and a phosphate. Our other piece happens to be a potassium and a chloride. Now, can you make magnesium phosphate look good for me? What's the charge on that?
Magnesium is a +2.
Okay, phosphate?
Phosphate is a -2.
-3.
-3.
So least common multiple?
6.
Okay, so give it to me.
All right, so you need, oh, I'm struggling with this one.
So you have a +2 with the magnesium here. How many of those do I need to make a +6?
3.
Yeah,
3 of
because
them.
2 times 2 is 6. And then how many phosphates?
2.
2, because 2 times 3 is 6. Okay. Potassium and chloride, I will go ahead and just remind you it's a +1 and a -1. That is A-OK. The magnesium phosphate, I'm going to say that is my solid, and my potassium chloride is an aqueous for reasons that we will see in a couple of Mondays. Now, not to put too fine a point on it, but if we take a look, don't do that. If we take a look, we have one magnesium on the left, we have 3 on the right. So I will start with 3 magnesiums on the left, but that screws up my chlorines. How many chlorines do I now have on the left?
6.
6, because 3 times 2 is 6. I'm going to come over here and put a 6 on my KCl, but that screws up my potassiums. How many potassiums do I have?
3.
We put 2.
I have how many?
You have 3.
You
Put
have 3, you need 2.
I have 6 on the right.
Yeah.
I need 6 on the left. I already see 3 of them, so I'm going to put a 2 in front.
Mm-hmm.
Now, how many phosphates does that give me?
8.
2.
2.
2 phosphates.
2.
2 of the
Yeah,
PO4s,
2.
because I see
Yeah.
the 2 right there.
Yeah.
And guess what? We're good.
Yeah.
I want to point out that aside from combustion reactions, you will not go above 6. Okay? You will not go above 6 unless it's a combustion. In all of the ones that we have done right now, with the decomposition, single, double, and now neutralization coming up, you will not go above 6. If you're going above 6, you're doing something wrong. Okay? Let's go ahead and do neutralization. And then I'll talk briefly about something else, and then we'll end the recording and stick around for after class questions. So neutralization. Almost done, guys. Neutralization. This is an acid and a base, and they're going to make water. Make salty water. I'll start out with the trivial one, give you a less trivial one, and then we'll make some announcements and call it a day. So, good old HCl, since it's an acid, I better put an AQ. Good old sodium hydroxide, also aqueous. If we look at this reaction as I have written it, what kind of reaction does it look like? I bet someone could.
Replacement.
Yeah. Oh man, you missed it. I was gonna say, I bet someone could double down.
Sorry.
There's the sodium.
All right. I should have been faster on that. But as my son has been reminding me, as Daddy gets old, he gets slow.
Sodium chloride and H2O.
Yeah. So this does still look like a double replacement. It looks like the H goes to the OH and the Na goes to the Cl.
Mm-hmm.
So on the other side, you'll make NaCl, which of course is soluble, and you'll make good old-fashioned HOH, which is a liquid.
What are you writing?
What? What's that, Winnie?
I thought it was H2O.
Oh, I know, you're wrong.
Huh?
No, check this out. Check this out. H2SO4 AQ. I'll show you why I'm doing it. Plus potassium hydroxide, KOH, aqueous. On the other side, again, this is going to look like H to the OH and the K to the SO4. I'm going to go ahead and, spoiler alert, it's K2SO4, aqueous, and a couple of HOHs liquid.
So what is the underlying principle for that?
Okay, the underlying principle of that, ease of balancing. That's what it's all about. If you take a look on the left-hand side, we could say, oh, well, how many hydrogens do we have on the left-hand side? We have 3. How do you get 3 and this other thing to work out? You don't worry about that balancing the 3s. You say, look, what do I have? I have an OH and I have an H. Why don't I just balance those? And so in neutralization, HOH is advantageous to write because I can see that I have my one OH and one OH. Great.
Mhm.
I have my two H's on, oops, my two H's on the left and only one on the right, right? Only one. That's why I'm going to put two H's, but that now gives me two OH's. I'll put a 2 there, which is good because that balances out my potassiums.
All right. Would that be different if it was a chemical reaction?
This is a chemical reaction, right?
Mm-hmm.
So your question is, well, I guess, why don't you see this as a chemical reaction?
Yeah.
Why
I
don't you?
think so. Because I see HOH, and I would think HOH would be an H2O.
Yes, that's fine. And if you want to write H2O, that's fine.
Okay,
I'm
that's
just
where my
saying
problem was.
You'll spend extra time balancing, not too much extra time, but some. So don't worry about it. If
Okay.
the HOH bothers you, forget it and just write H2O and balance it.
All right, thank you.
And you'll be fine. I'm going to go ahead and make the note though. In neutralization, HOH helps you balance. In neutralization, using HOH helps to balance. All other times, use H2O. Okay, so those are all the reaction types that we have. You'll be seeing all of these as you do the videos labs that Josh and I made for you guys. And so I highly encourage you guys to practice those by going through and trying to do the post lab and trying to balance them and predict them. When we come back Monday, I'll tell you a little bit more about how those singles and doubles occur. And we'll do a few more examples of the types of reactions then. I do want to address the exam and the labs. So this is just a thing. We're all still working out the kinks. This afternoon, I have an online appointment with one of our specialists to help me help you. I've figured out why some of you had a hard time submitting your work, because some of you made an 85 megabyte PDF to send to me. Yeah, an 85 megabyte. Now, we have to get that size down so that it doesn't clog up the internet, for one. For two, take me 3 minutes to download your PDF, which that does given my internet connection. I'm gonna try to find a way to make a video or some sort of written tutorial to say, look, when you take your 11 megabyte picture and you email it to yourself, you probably want the small or maybe medium version of it to make it small enough that the PDF is not a behemoth. The other thing is also, please, 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 that video that Reagan and I made, we said, when you have that file, please save it with your name and the assignment in the title of the file. I'm downloading your stuff right now, and I just keep seeing exam 3, exam 3, exam 3, and I'm having to go through and rename all your files to try to keep you straight when I go to open it and try to grade it. So please rename your files so that it says, you know, Reagan Hence exam 3 or April Sanders lab 7. So that when I'm looking at them or downloading them, there's no question at whom I'm looking. Does that make sense, guys?
Yeah.
Yes.
Okay.
Yes.
Yeah.
With that, I'm going to go ahead and I'm going to stop sharing here, and I'm going to go ahead and stop recording. And I'll stick around for after class questions, unless someone's got a burning one right now. Stop recording.